Welcome, ladies and gentlemen. My name is Brian McLogan, and in this video, I'm going to show you how to solve rational equations. Now, this is actually the last and final section in our chapter on rational functions for my pre-calculus class. So what I'm going to do is I'm just going to kind of work through my notes and kind of work through some of the answers and show you some of the work that we did in class. So therefore, I can kind of round out all of the examples, and I hope to also help you along with understanding how we want to approach solving rational equations, as well as the process to do that. So what I did though was, at least in my classes, I start off with my students, giving them like 3 minutes to see how many of these equations they could go ahead and solve. Obviously, I didn't give them the work, but what I did was I provided, basically gave them and said, go and work. Now, a lot of students, they do the first problems rather easy, but then once they started to see more and more fractions, they started to slow down. They started to do fraction operations. So the work that I showed is basically by me multiplying by the number 2. And if you notice, at least in the first 6 examples here, 2 is what we call the least common denominator. If you multiply every single term by 2, you would get rid of the denominators, right? So this is something that we talked about in previous sections, that, if we want to get rid of our fractions, we can multiply by this common denominator, or we talked about it when we were simplifying complex fractions. For instance, like look at f. If I multiplied everything by 2, not only am I going to produce an equivalent equation, but now I'm just going to have the equation x plus 1 equals 3, and that's easy to solve, right? The LCD does change here as we get to G, H, and I. You can see that here it's the product of my denominators, 2 times 3, which is the LCD is 6. So therefore, I multiplied everything by 6 here. Here again, the LCD is 6. You're not going to want to multiply 2 times 3, then times 6, because you can see that 2, 3, and 6 all divide into 6 in this example. And then again, in this example, you can see that the LCD was 12. So that's what I multiplied by, and then just simplified, and it made doing the work a lot easier. And then I kind of worked my way up to, for my students, as far as getting, well, what about if we have some variables in the denominator? So kind of did the same thing, gave them like 3 minutes and said, all right, let's go ahead and see how far you guys can get. And from here, we kind of worked on some, certain understanding that we needed to know when we're solving for equations when our variable x is in the denominator. And one is we can't have our variable in the denominator, right? We have to get the variable off the denominator. Now, you could just multiply by the LCD in this case, for this example. You can multiply by the LCD, but the other way, I'm not sure why I actually did that example this way. But if you subtracted the 1 to the other side, you get 2 over x equals 2. Well, again, to solve for x, you're going to want to multiply by x on both sides, right? So therefore, you'd have 2 equals 2x, divide by 2, x is equal to 1. So that is another way to approach that first problem. But basically what I was showing my students is, use inverse operations. Like for these first 2 examples, we can just go ahead and apply inverse operations to go ahead and solve. It's, the main thing is after we subtract the 1, once we've isolated now our fraction, I just multiply by my denominator on both sides, make sure you keep the parentheses so you do distributive property, and then you can go ahead and solve. But that worked when we had one fraction. And you can see that once we start having more than one fraction, inverse operations don't really become as ideal anymore. Like what inverse operations are you going to want to apply here? Now, in this case, I actually multiplied by the LCD on both sides. And I'm not sure why. I guess I just didn't show that. So each one of these, I can multiply. So here, I basically multiply by my LCD of the product of these two, x times x plus 2. Whereas here, my LCD was equal to 2x. Here, my LCD was equal to 2x. I did these very, very quickly as well. Here, my LCD is equal to 2 times x plus 2. Okay, so that's what basically I was multiplying everything by when I was go ahead and solving these. So that's what I multiplied. That's what I multiplied each of those equations by to get to my second equation. Now, obviously, again, this was for some practice versions. So I did slow down and teach my students K, O, and Q so they could kind of see how things were working out. We didn't talk about excluded values in this case, or checking the solutions, because obviously that's going to be a part of our curriculum. But the main thing that I really wanted students to come away from this is if you can identify the LCD, notice how the second step in every single one of these problems is all an equation, right? There's no more fractions anymore. So by multiplying by this LCD, I eliminate my fraction. And that's very important. And then we kind of end it here with getting to R, on the R. And when R, what we notice is this is the only example where I actually got two solutions. And therefore, when I plug in those two solutions, because remember, like if you find a solution and it's going to make sure that equation is true. So when I plug these values back in to like make sure it satisfies them, I recognize something that's interesting. -2 actually makes this fraction's denominator 0. Well, that's undefined. That doesn't work, right? So therefore, that is what we call an extraneous solution, which we move down. So then that prompts me to say, well, whoa, let's make sure we go back and check to make sure any of our other solutions weren't originally excluded values. And it's a really quick check, and you can see that none of the other values or problems that we did had an extraneous solution. So therefore, we just need to really understand what it is this extraneous solution is. So extraneous solutions are basically a solution to a simplified version of an equation that does not satisfy the original equation. So let's look back at what we have. So I had 2 over x plus 1 over x plus 2 equals 3. That is my original equation, right? Now, obviously, when I multiply by the LCD, I get this nice, lovely quadratic that looks like this, 3x squared plus 3x minus 4. Now, forgetting about the original problem, if I was just going to look at simplifying this this equation, like that's from, Algebra 1, Algebra 2, I can just go ahead and factor that, to go ahead and solve quadratic formula, factoring, whatever may be the case. But I am going to have two solutions here. And so even though these are two solutions for this equation, when you plug these values back into the original equation, you recognize that they make, or at least -2 makes this fraction 0. So like you can see that 2 over x plus 1, oops, let's do this. 2 over -2 plus 1 over -2 plus 2 does not equal 3, right? Because that is a no-no. I'll just write undefined. So that's undefined. So of course it's not going to equal 2. So if it satisfies the simplified equation, but it does not satisfy the original equation, that's why x equals -2 is extraneous. And when I mean extraneous, it just means it's not a solution at all. Okay, so a lot of times we'll find it as a solution, but if your only answer is extraneous, then you have no solution for your equation. And we will cover, and we will have some problems like that as well. So then I kind of went through two examples for my students. Basically just kind of reminded them, so the main idea here is basically identifying the LCD, multiplying our equation by our LCD to eliminate my denominators. Like notice how each one of these, right, now does not have a denominator, right? And then I just keep on simplifying to solve. Make sure you notice the difference here between my linear equation, right? When linear equations, that means x is raised to the, to the first power, right? So you can just combine like terms, get the variable to the same side using inverse operations and solve. Obviously, make sure you check -13, make sure that it's going to work. But that's kind of it. The difference here is in the second example, when I multiply by my LCD, my simplified equation is not linear. It's not like this. It is a quadratic. So that is a different process that we need to do to solve quadratics compared to linear equations. And a lot of students, since we, once they get used to doing linear equations, they kind of totally forget what we did for quadratics. Quadratics has a x that's squared and a linear x, right? Or not all quadratics, but at least, for it to be a quadratic, you have to at least have an x squared. If there was only one x squared, you could use inverse operations. You'd have to use the plus or minus form, but you could use inverse operations. But whenever we have an x squared and the x, a linear x, we have to either use factoring, completing the square, or quadratic formula to go ahead and solve. And that's where a lot of students made their mistake in my class on their quiz, is they kind of completely forgot how to solve quadratics. But in this case, this one was factorable, but I recognize that I get my two solutions, x equals 6 and x equals -1. However, going back to the original equation, you can see that 6 makes my original equation undefined, so therefore it is extraneous and not an actual solution to the equation. All right, so let's go and take a look at kind of solving some equations here, and kind of based off the way that I have kind of taught. So when we're identifying the LCD, we're looking for factors that they have in common. Really, y plus 1 and 3 do not have any factors in common, so I am just going to multiply by my LCD on both sides. Okay, by doing that, you can see that my y plus 1's divide out, leave me with a 3y. And here, my 3's divide out, leave me with a 2 times y plus 1. And obviously, as you get a little bit more familiar with this, you can distribute that 2y plus 2. And then let's get the y's to the same side, and we get y is equal to 2. And obviously, you can now go back to your original equation and say, yeah, that makes sense, that works. For the next example, you could say, well, I don't really feel like multiplying these two denominators. That kind of looks a little crazy, doesn't it? And that's true. It is a little crazy. So first thing we want to do is factor them. So if I have x minus 1 times x plus 1, and then over here, I need to have, let's see, that's going to be x plus 2 times x minus 1. So here they do have a factor in common, which is the LCD, which is x minus 1. And then the factors they don't have in common is going to be x plus 2, or x plus 1, I'm sorry, and x plus 2. Okay, so now we have an LCD of 3 terms. Now, again, you can do it just like this one, but you can see like this is a lot of writing, right? So after this, I'm going to give you a little bit of another way to do this that's a little bit easier that you can understand. And obviously, once you kind of work through a lot of these examples, there's some other shortcuts that hopefully you'll kind of identify as we keep on doing more and more of these that will make your life a little bit easier. But first of all, we see that when doing this, the x minus 1's divide out, the x plus 1's divide out, just leave me with a x plus 2. And then on the right side, my x plus 2's divide out, my x minus 1's divide out, leave me with a 2 times x plus 1. Well, now, again, I can go ahead and distribute. Okay, and then let's just get the x's to the same side. And therefore, you get x is going to equal 0. Now, some of you might have already been saying, you already recognize this and say, oh, do the cross product, cross multiplication. And yes, that actually works as well. I don't teach it, I allow it. I don't teach it to my students just because from my experience, what I noticed, in a chapter like this, where we're multiplying, dividing rational expressions, as well as solving with multiple fractions, people misuse cross multiplication all the time. You can only apply the cross product when you have a proportion, basically a fraction equal to a fraction. And these are the only 2 problems that we're going to do in this lesson where you could have applied the cross product. And basically what the cross product allows us to do is just multiply directly across. Again, we have a fraction equal to another fraction. So if I go ahead and apply the cross product, then I'm going to have 2x squared minus 1 is equal to x squared plus x minus 2. Now, again, you could also have a good debate as far as saying, I'm not sure if that is actually easier now than if it was just to multiply by the LCD. Sometimes the cross product is, like over here, if you were to apply the cross product, you would get 2 times y plus 1 over, equals 3y, which is exactly the same process that we just had. Right now, obviously, I showed a lot of work because I'm teaching, but you could do this exact same stuff multiplying by the LCDs and not show as much work to me. But it's important for us to kind of see the difference here, at least in this problem, as far as what happens when we find the cross product. Because in the first example, applying the cross product to LCD is not going to make a difference. But here, I'm actually going to get a different answer, which is kind of interesting here. X squared, I'm just going to have to subtract an x, and I'll have to add a 2 to both sides. So by doing that, I get 2x squared minus x equals 0. Factor out the x, and I get x minus 1, x times x minus 1 equals 0, so I have x equals 0 and x equals positive 1. So this is weird. By applying the cross product, I have now 2 solutions, whereas the original equation, I only have 1 solution. So, what is the correct one? Which one is, which one should we use? Well, the important thing is we recognize if we were to take 1 and plug it back into the equation, we recognize that that is an extraneous solution. So in this case, we don't need to label any of our extraneous solutions. We only had 1 solution and it worked, so we are good. Whereas this case, if we solve by this method, we have to make sure that not only we have to solve for 2 solutions, but we have to recognize that the x equals 1 is also an extraneous solution. So we'd have to label it as such. So that's kind of how those problems can differentiate there that you want to make sure that you're aware of. So, If you prefer cross multiplication at all times, I mean, go for it. I think though, you multiplying by the LCD and not showing as much step-by-step work can be just as fast as well as easy as cross multiplication. And again, the other major thing that I see students do is they misuse it. They like cross multiply right here. And I'm like, no, that's the reason why I don't say cross multiplication. That's the reason why I don't teach cross multiplication. Cross multiplication is only when you have a fraction. So let's do it like this. When you have a fraction equal to another fraction, okay, which we call a proportion. Therefore, A times D is equal to B times C. So, I mean, it's perfectly fine, but just don't use it when you have more than, when you don't have fractions adding or subtracting or multiplying and dividing, or you have like, 3 or 4 fractions. Don't be trying to do anything crazy. All right. In the next example here, you could just multiply by the LCD, which would be my preferred method. However, we do recognize like these both have the same denominator, right? So couldn't you just put them under like x minus 1 equal to 4, right? Is there anything like wrong with just combining numerators here? And then you just multiply by x minus 1 on both sides. Therefore, you'd have 2 plus x equals 4 times x minus 1. Now, in my preferred terms, I'm just going to say the LCD is x minus 1. So if I multiply everything times x minus 1, the x minus 1's divide out, leave me with a 2. Here, the x minus 1's divide out, leave me with an x, equals 4 times x minus 1. So you can see like it's the same idea. Like there wasn't one that would have been easier. I mean, maybe easier than the other, but you're going to get to the exact same equation. So now let's just go ahead and distribute here. So I'll just solve this one just to kind of choose for x minus 4. And then let's get the x's to the same side and get the numbers to the same side. So the 6 equals 3x, divide by 3, flip it over, and we get x is equal to 2. Plug that back in, and we can see that that is not extraneous, so we're all good. And next example, we only have one denominator, and it's a variable x. So I'm just going to multiply everything times x. And again, it's very important to make sure we multiply everything times x. Because, that is going to produce what we call an equivalent equation. Okay, so now I recognize I have a quadratic. It's not in standard form though, so I'm just going to rewrite it in standard form. And now I say, okay, so now I can either factor this, quadratic formula, complete the square, and I say, all right, what two numbers multiply to give me 12, add to give me -8, and I'm thinking 6 and 2, -6 and -2. Therefore, we can say x equals 6 and x equals 2. All right, so on to the next example. So now we have a couple more fractions here. But again, like the same idea here. Again, we don't want to just multiply. We see that these are the same. So a couple different ways we could do this one. If you love cross multiplication, then obviously you could go ahead and say, well, why don't I just add the 2 over x plus 2 to the other side? So therefore, you would have, 3x over x squared minus 4 equals, let's see, add a 2, so that's going to be a 3 over an x plus 2. However, if you were to do it this way, I will let you know that you are going to get some different solutions than if you just multiply by the LCD. So again, it's just making sure that you understand your solutions or your process here. You can apply the cross product if you like, right? However, my idea, guys, is to understand, well, what do these have anything in common? By factoring these, I see this is x minus 2, x plus 2, right? I'm actually just going to delete that. I did have some students went and do that. They love cross multiplying, so I'm like, that's fine. Just make sure that you're going to get the same answer, obviously, as me. And as long as you're applying cross multiplication, okay, or in the right context, and then I'm fine with it. But you recognize now the LCD, what they have in common is x minus 2. I'm sorry, x plus 2. What they don't have in common is an x minus 2. So therefore, I'm just going to list that as x plus 2 times x minus 2. So again, multiply everything times this LCD. And you could write it as a product of each and every one of those, but obviously to save myself some time, I am not going to do that. So, we just multiply these. You can see though that whatever's in the numerator is in the denominator. That's why I don't have a denominator anymore, right? It got divided into it. Whereas here, only my x plus 2 can divide into that. So therefore, that's going to leave me with an x minus 2. Be very careful to keep check with that negative. So that becomes a negative 2 times x minus 2, right? Because the x plus 2 is divided out. Here again, the x plus 2 is divided out, so I'm left with a 1 times x minus 2. I don't need to be as careful with a 1 as far as my distributive property, but it's very common for students to make a mistake here with that negative 2. All right, so now we can go ahead and distribute. And then we just need to get the x's to the same side. And we get something very interesting. 4 is equal to negative 2. Well, that's kind of weird. Again, we're trying to find solutions, and then we get a statement that is not true. So what does that mean in the context of the problem? That means there's no solution. And if you were to have done that original equation or the original problem, you only would have gotten one solution, and it would have been extraneous. So therefore, that's another way for you to receive no solution. So that was kind of important here about that question E. That was a way for another way. If you see the cross multiplication, if it would have been easier, you still would have gotten no solution. You would have got one solution, but it would have been extraneous. In the next example, hopefully you guys can recognize that my LCD here is going to be x minus 1 times x plus 1. So multiply everything times that. And by multiplying everything times my LCD, I just have to write it out there. My x minus 1's divide out, so let's leave me with 2 times parentheses x plus 1 equals, now 1 times x minus 1, x plus 1, let's actually, multiply that out, right? Like what is x minus 1, x plus 1? That's x squared minus 1. So typically I don't really, we like the things in factored form, but obviously if you're multiplying by this number, let's use that simplified value. So x squared minus 1, and then minus, here we're going to have x plus 1's divide out, so it's going to leave me with an x minus 1. Again, being very careful with that negative and parentheses. Okay, let's use distributive property here. 2x plus 2 equals x squared minus 1 minus x plus 1. Let's subtract the 2x to both sides. Let's subtract the 2 to both sides. So I get 0 equals x squared minus 3x. And then let's see, that becomes a negative, what's a minus 2? Is this a problem? I kind of forgot about this example. Yeah, that is the answer. Okay, so that becomes a negative 1, or that becomes 0 minus 2. Okay, so now we say, all right, let's go ahead and factor, right? And then we recognize and we say, crap, this is not factorable. There are not any two numbers, at least real integers, or rational numbers that multiply to give you negative 2 and add to give you negative 3. So therefore, when we have a quadratic set equal to 0, we can now use the quadratic formula. So in this example, what I'm going to do is I'm going to have x equals opposite of b plus or minus the square root of b squared minus 4 times a times c all over 2 times a. So that becomes 3 plus or minus. Let's do some math in our head here. Negative 3, that's squared. Negative 4 times negative 2 is a positive 8. 9 plus 8 is 17. Divided by 2. And obviously, obviously it's pretty obvious to note that neither of those answers, when you plug them in, is going to make my denominator 0, because the only numbers that make my denominator 0 are going to be 1 and negative 1. So therefore, that's neither of those. Those are your solutions, which are irrational. Perfectly fine. Just make sure you can apply the quadratic formula if it is non-factorable. All right, so let's kind of continue on. So you can see this one's kind of same here. But again, this is another factored form, n minus 1 times n plus 1. So multiply everything. Okay, and what we get is we like the 1s here. We don't have to worry about distributive property. Here we get a 2n equals 2. Divide by 2, n is equal to 1. And again, we recognize when we plug in 1, that gives us, when we plug in 1, that gives an extraneous solution, right? So since we now have an extraneous solution, this is another example of no solution. So we can get a no solution here from, getting a statement that is incorrect. Or actually, if we go ahead and solve and we only get one solution, but that one solution ends up being extraneous, therefore then it's going to be no solution. For the next one, we see a trinomial as my denominator. So let's go ahead and factor that here to n. Let's see, that's going to be a -8. So that'd be n plus 4 times n minus 2. Now, I had a little trouble factoring this, right? I kind of like thought about that for a second. But the important thing is, like, I have two other factors, or two other denominators here. It's not always the case, guys, but it's a good tip to look at these other two denominators, right? Because when you're trying to identify the LCD, and you saw in that second example, if you have three factors, like if this was factored not including these two numbers, you would have four factors in your LCD. That's going to create a very complicated problem. Even 3 factors in your LCD is going to produce a large problem. So it's not always a guarantee that, you know, the factored form of this quadratic is going to be these two denominators. But the more factors you have in your LCD, the more complicated the problem is. So if you have something you need to factor, I would definitely look at those other two denominators, because they're either both going to be the factored form of that, or at least one of them is going to be have some shared factors in that case. So, because otherwise the problems are just going to get so big, it's just not going to be, you know, worth it to like be doing the math on it, because it'll just take so much time and so much algebra to go through. All right, so here's my LCD. Multiply this by every term. So you can see the n minus 1s are going to divide out. Here you can see my n plus 4 and my n minus 1s would divide out, 2n plus 1. Plus here you can see my n plus 4s divide out, so that'll leave me with a 2 times n minus 2. But don't write it like this, right? Because you want to make sure you use the parentheses. And that's just a very big mistake. People write it like that, and then they'll have it as 2n. And they'll have 2n minus 2, but it's not 2n minus 2. It's 2n minus 4, because you have to apply distributive property. All right, so let's subtract the 1 here, and then let's combine like terms. So I have 0 equals 4n minus 3. Add the 3. 3 equals 4n. Divide by 4. Divide by 4. N equals 3/4. Okay. And yep, there you go. One solution. Just make sure it checks, verifies, all good. All right, we're almost done, guys. We're just keep on working on through there. You can see a lot of the same thing over and over. Like, my main goal is just get rid of these fractions, simplify, you know, and simplify and solve, and then make sure that I understand the solution in its context of the problem. So here I recognize another difference in 2 squares. I'm going to multiply everything times that LCD. Oh, this is n, right? Sorry. Did I do that up there? No, I didn't, but that's okay. Yeah, that's what I'm just gonna move that over to save myself some time. All right, so when I multiply it here by this first term, you can see my n minus 3, my n plus 3s divide out. So that's just going to leave me with the 4n squared, minus my n plus 3s divide out, leave me with a negative 2n times n minus 3, equal my n minus 3s divide out here, leave me with a 3 times n plus 3. And again, don't write it like that, use parentheses. All right, so let's go ahead and do some distributive property. 4n minus 2n squared plus 6n equals 3n plus 9. Let's get the 3n to the other side. Let's get the negative 9 to the other side. So I get a negative 2n squared. That becomes a 3, so that becomes a positive 7n minus 9 equals 0. Now again, if I was going to factor this, I don't want that negative in front, right? But I do want that negative. How do I get the negative 9? I don't remember this being the problem. Let me just double check and make sure I did my correct. What happened to the 4n squared? Ah, that's where I made a mistake. I forgot to put the square there. Because I was like, I remember doing this problem. I don't remember having that as the example. So 4n squared minus 2n squared is a positive 2n squared. that becomes a plus a 3n minus 9 equals 0. Okay, so now we got to see, is this factorable, right? So we know that this is a quadratic trinomial, so since it's a quadratic, we know that it can be factored into a product of two binomials. And I know those coefficients here are going to be 2n as well as n. And we want to multiply to give us -9, but we were looking for a difference of our products to give us 3n. So I'm automatically thinking of positive 3 and negative 3, right? And again, if you multiply this out, just kind of doing this in your head, you can see that this works. So therefore, I use the zero product property to set them both equal to 0. And then I can see n equals 3/2, and n is equal to -3. So, therefore, now let's go and check our solutions, make sure that they both work. And however, when I plug -3 back into this equation, you can see it's going to make this fraction 0. So therefore, that is extraneous. And there's only one solution, positive 3/2. For the next example here, in this next example, again, we want to see, well, I think this factored form might be like this, right? So x plus 2 times x plus 3. And again, that does work. So therefore, I'm going to multiply everything times x plus 2 times x plus 3. And by doing that, I get 3 plus x minus 1 times x plus 3 equals 7. X plus 3 is divided out, leave me with an x plus 2. Okay, so now in this case, I need to go ahead and use FOIL, right? Multiply these out. So that's going to give me 3 plus, when you multiply that out, they give you x squared. I'll just do it out. That gives me a negative x plus 3x minus 3 equals here, distributive property, 7x plus 14. Now let's just go ahead and combine like terms here. So let's see, those are going to add to 0. So left with x squared plus 2x equals 7x plus 14. Let's subtract those on both sides. 14. So that's going to leave me with an x squared. Let's see, minus 5x minus 14 equals 0. And again, now we want to make sure that we can see this to be factorable. And I see that, yeah, I can do this as x minus 7 times x plus 2 equals 0. So therefore, x is equal to 7 using the zero product property, and x equals -2. However, when you take x equals -2, you plug it back into the original equation, you see it does not satisfy that. So therefore, x equals -2 is an extraneous solution. So that's basically what we did, ladies and gentlemen. I covered a lot of different examples for you to be able to how to solve your rational expressions. And you can see it's basically the same thing over and over and over again. I really like to multiply by that LCD to get rid of the fraction, because I think that just makes all these problems really kind of basic and easy for you to go ahead and solve. However, that process that we did for that is also the same process that I want to remind you of what we covered in the first unit, which was complex fractions. So when I first taught complex fractions to my students, it was kind of at the end of class. We already had added, subtracted, multiplied, divided, and students were kind of a little fatigued. And even though I taught it to them, I know complex fractions is probably something that they do not have a lot of experience with, and they really need a lot of practice to go ahead and simplify. So what I decided to do was to teach it again, kind of like reteach it, or at least just give them more practice on this, because really complex fractions is related in terms of operations with the add, subtract, multiply, divide, and simplify that we did in the first day of this lesson. But it's also very similar to this lesson because the steps, the process that we're doing is exactly the same. We are multiplying by the LCD to eliminate our fractions, right? So when I multiply by x minus 1, I eliminate my denominators, x minus 2, or x minus 1. When I multiply by x minus 2, I divide out my denominators. So therefore, I only have one big fraction. Whereas here, when I multiply everything times x plus 3 times x plus 4, I get rid of all my fractions. I get rid of all those little fractions because they all divide into their terms. And then I can just go ahead and simplify. The only thing that we didn't talk about in day one, which I wanted to bring up to my students today because we have a little bit more time on this, is understanding the restricted values based on the fraction. And not only do the denominators here, when we know that, x cannot equal 2, but understanding the restricted value in the denominator. So here you can see this is 3x minus 7. So therefore, we got to set that equal to 0 and, solve. And obviously, that's going to give us a value of 7/3. So x also cannot be 7/3. So it's not just the original problem for excluded values. You also want to look at the final simplified problem for your excluded values. All right, so I'm just going to cover 1, 2, I think 4 more examples. Yeah, so just 4 examples of just practicing this, so therefore students can feel more comfortable. So we're going to simplify as well as identify or label the excluded values. All right, so the first one here is I recognize my LCD is just the product of my denominators, which is a 3x, right? The 3 and the x don't have any factors in common, so I'm just going to multiply everything by 3x. And when doing that, I get 3 plus x over 3, x minus 3. And you can see how everything, 3x times 1/3 is just going to give us x. 3x times negative 1 over x is just going to give us a negative 3. Now, obviously, we know that as far as excluded values go, in the original problem, x cannot equal 0. In my simplified problem here, I know that x cannot equal 3. So you can see how that simplified problem actually produces an additional excluded value. I factor this here just to make sure that it is the same, which it is. So therefore, my LCD that I'm going to multiply everything by is going to be x minus 1 times x plus 1. Okay, so I multiply that by the first fraction. The x plus 1's divide out, leave me with 2 times x minus 1. Here, my x minus 1's divide out. That's going to give me, what is that, a plus? Plus x times x plus 1. And then over here, those terms divide out, just leave me with a 3x. So now let's go ahead and simplify that using distributive property. So I get a 4x minus 2 plus a x squared plus x all over 3x. And then I could just, rearrange this one more time. X squared, those combine to give me a 5x minus 2 over 3x. Now again, going back to my original problem, we know that x cannot equal negative 1 and positive 1, so I'll just do plus or minus 1, as well as 0. All right, next example. You can see here, this is kind of interesting. These we have every single thing is different. But if I factor this, then that's going to give me an x times a x plus 2. So it has an x in common here, and it has an x plus 2 in common here. So therefore, my LCD is going to be x times x plus 2. And again, this would be 1, right? So the fraction. So if I multiply x times x plus 1 times our first term, well, that denominator is going to divide into that. So that's just going to be with a 1. Minus here, my x's will divide out. So I'll be left with a 2 times x plus 2. Here, my x plus 2's divide out, leave me with a 3x squared. And then here, nothing divides out, so that's going to leave me with a negative 2 times x times an x plus 2. Okay, so now let's go ahead and see how everything simplifies. So I get a 1 minus 2x minus 4 all over a 3x squared minus a 2x squared. And that'd be a minus a 4x. Right? Because you got to make sure you apply distributive property there. And you're multiplying the negative 2 and the x. So let's simplify that one more time here. So that gives me a negative 2x minus 3 all over 3x squared minus 2x squared. It's just going to give me an x squared minus 4x. Now, again, factoring that, or setting that equal to 0, you get an x times x minus 4 is equal to 0. So x equals 0 and x equals 4. All right, so looking at my restricted values, I know x cannot equal 0, right? I know it cannot equal negative 2. This is just a combination, this is just a combination of those two factors. So the only thing added now is going to be a positive 4. But you can see we have 3 restricted values. All right, last example here. Very, very similar common denominator. In this one, though, we can see if we do our math, we factor this, then it's kind of like this exact same type of problem. We're going to have x times x minus 1. All right, so when I multiply that times my first term, my x's divide out, leave me with a x minus 1. Here, my x minus 1's divide out, so that's going to leave me with a minus, I'm going to use parentheses, x plus 1 times x. Now, you could put the x in front if you wanted to. That might be a little bit easier. Let's actually do that. It's just going to be easier to distribute that way. All over here, my x minus 1's divide out, leave me with a 3x squared. And then here, everything divides out, leave me with a positive 1. All right. Combine some like terms here. I get x minus 1 minus x squared minus x. That goes to 0, so I'm left with a negative. Oops, sorry. Should probably. Now let's rearrange the terms. That goes to 0, so that's a negative x squared minus 1. Here we have a 3x squared plus 1. Now, you could, there's really nothing else that we can really do to simplify this. So let's look at our excluded values here. We know x from the original problem cannot equal 0 and x cannot equal 1. But then we want to set this denominator equal 0 like we did over here, right? But something interesting here again happens. When I set 3x squared plus 1 equals 0, well, I get a 3x squared, equals a negative 1/3. Well, now if I want to go ahead and take the square root of that, well, that's going to be in my complex number system. So I don't need to exclude complex numbers. I only need to exclude real numbers that make my denominator equal to 0. So hopefully that helps you guys out as far as, now that we looked at complex numbers or complex fractions first in the first lesson with, operations and simplifying, to now looking at complex fractions in the last lesson with solving, where we multiply by the LCD. And that's really, where it kind of comes down to for solving these is simplifying these expressions. So therefore you don't have as many fractions. And, from the beginning of this lesson, when you eliminate as many fractions as possible, you're making your life a lot easier. But it is important to make sure that we still understand our excluded values, especially when we are solving, because when we're solving and we have a solution that is an excluded value, it is an extraneous solution and actually not a real solution to the equation. So there you go, ladies and gentlemen. That is the last section in rational expressions. I hope you guys enjoyed, and I look forward to seeing you guys in the next video.